NASA is quietly killing off traditional chemical rockets to build an interplanetary nuclear freight train set to launch to Mars in just 2 years. For decades, we've been told that a human mission to the Red Planet was a distant dream, a goal for the 2040s. But in March 2026, the agency dropped a bombshell that changed everything. The mission is called Space Reactor One, and it's not just a proposal, it's under construction right now. I'm your host, and today on Astro Trivia, we're breaking down the physics, the logic, and the sheer audacity of NASA's nuclear leap to Mars. To understand why NASA is betting the farm on nuclear energy, we first have to look at the massive wall we've hit with chemical propulsion. We've been using the same basic technology since the Apollo era, and frankly, we've reached the limits of what physics allows. It's called the tyranny of the rocket equation. If you want to go faster or carry more cargo, you need more fuel. But fuel has weight, so now you need even more fuel just to lift the fuel you already added. It's a vicious exponential cycle that leaves us with rockets that are 90% propellant and only a tiny fraction of actual payload. Look at the current landscape. When we talk about landing massive payloads on Mars, the logistics are staggering. To get a heavy vehicle out of Earth's orbit using chemical engines, you don't just launch once. You often need dozens of separate tanker missions just to refill the tanks in low Earth orbit before the journey even begins. And even then, we are slaves to the orbital mechanics of the solar system. We have to wait for a tiny launch window that opens only once every 26 months. If you miss that window, you're stuck on Earth for another 2 years. This wait and coast method is slow and incredibly inefficient. It takes 6 to 9 months of drifting through the vacuum, exposing astronauts to prolonged cosmic radiation and bone density loss. For robotic missions, it means we can really send rovers about the size of a small SUV, like Perseverance. If we want to build a permanent base, or eventually a city, we can't keep throwing billion-dollar bottles into the cosmic ocean and hoping they wash up on the Martian shore months later. We need a system that functions less like a fragile explorer and more like a heavy-duty industrial railway. We need a way to move massive amounts of infrastructure without needing a fleet of 100 rockets just for the gas. That is exactly where the Space Reactor One comes in, marking the end of the chemical era and the birth of the nuclear frontier. The heart of this revolution is a machine that sounds like it belongs in a sci-fi novel, the Space Reactor One, or SR-1 Freedom. Now, when people hear nuclear rocket, they often think of nuclear thermal propulsion, where you flash heat liquid hydrogen and blast it out a nozzle. But NASA is taking a different, much more efficient route for SR-1, nuclear electric propulsion, or NEP. Think of it this way. Instead of using the reactor as a heater, they're using it as a high-output power plant. At the business end of the SR-1 sits a compact fission reactor. It's incredibly small compared to the massive cooling towers you see on Earth, generating about 20 kilowatts of power. For perspective, that's roughly the same output as a high-end backup generator for your home. It uses high-assay low-enriched uranium, or HALEU, which provides a massive amount of energy density in a very small package. The magic happens when that electricity is fed into a bank of massive ion thrusters. These aren't like the explosive engines on the bottom of a traditional rocket. Ion thrusters work by electrifying a DAS, typically xenon or krypton, until the atoms become charged ions. Then, using powerful electromagnetic fields, the engine flings those ions out the back at incredible speeds. While the push, or thrust, is very low, you couldn't even lift a piece of paper with it on Earth. In the vacuum of space, it's a game changer. Because it can run continuously for months or even years, the spacecraft keeps accelerating, eventually reaching speeds that chemical rockets could never dream of maintaining with heavy cargo. It's the freight train of space. It takes a while to get up to speed, but once it's moving, it can carry an unprecedented amount of mass with almost zero fuel consumption compared to traditional methods. To keep this miniature sun from melting the ship, NASA is employing a sophisticated heat pipe thermal transfer system. Imagine a series of closed-loop pipes filled with a specialized liquid. This liquid flows into the reactor core, boils into a vapor, and then zips through a turbine to generate electricity. As it cools down, in those large wing-like titanium radiators you see on the sides of the ship, it condenses back into a liquid and repeats the cycle. This closed-loop system is designed for zero maintenance. It can hum along in the cold dark of space for years, providing a steady, reliable heartbeat of power for the ion drives. But here's the kicker. How is NASA building this in just 2 years? The secret is a brilliant piece of engineering recycling. NASA realized that the propulsion and power element, or PPE, already developed for the Lunar Gateway station was about 70% of what they needed. By repurposing the Gateway's ion drives and electric architecture and swapping the solar panels with a nuclear core, they've bypassed a decade of research and development. It's the ultimate MacGyver move for the space age, turning existing progress into the engine that will finally unlock the red planet. So, what exactly is this nuclear powerhouse delivering to the red planet? You might be expecting a massive school bus-sized rover or a sprawling habitat module to roll out. But NASA is pulling a brilliant fast one on us. When the SR-1 Freedom arrives at Mars, it won't be deploying a traditional lander. There are no bouncy airbags like the Pathfinder days, and there is certainly no complicated rocket-powered sky crane lowering a billion-dollar rover on cables. Instead, NASA is executing a daring, high-speed maneuver, officially dubbed Skyfall. Picture this in your mind. As the spacecraft enters the Martian orbit, it drops a sleek, aerodynamic entry capsule straight into the thin alien atmosphere. This pod uses a robust heat shield to survive the blistering temperatures of atmospheric friction. Once it slows down enough in the upper atmosphere, a massive supersonic parachute violently deploys, yanking the capsule back. But here is where it gets absolutely crazy. It doesn't ever touch the ground. While still plummeting through the air at a relatively low altitude, the heat shield falls away, exposing the payload inside. 3 advanced helicopter drones, heavily upgraded versions of the legendary Ingenuity chopper that made history back in 2021, will instantly activate in mid-air. Their rotors will spin up, biting into the thin Martian air, and they will literally fly themselves out of the falling capsule. It's a spectacular, self-deploying swarm, scattering into the Martian sky before the empty outer shell even smashes into the dirt below. Why use helicopters instead of rovers? Because speed and coverage are everything right now. We don't have years to let a rover slowly crawl across a few miles of rock. We need answers, and we need them fast. These 3 Skyfall drones are our advanced scouting party. They are the high-speed reconnaissance team tasked with doing the dirty work before human boots ever touch the regolith. Each of these flying scouts is packed with cutting-edge technology, including high-resolution terrain cameras and, crucially, ground-penetrating radar. As they sweep across the rusty landscape, they have 2 primary objectives. Above ground, they're hunting for the perfect, flat, hazard-free landing zone, capable of supporting a massive crewed lander. Below the surface, they're scanning for the absolute holy grail of space exploration, accessible water ice. Water isn't just for drinking. If we find subterranean ice deposits, we can mine it, melt it, and use nuclear power to split it into hydrogen and oxygen. That means we can manufacture our own breathable air and rocket fuel right there on Mars, ensuring our astronauts have a guaranteed ticket home. The Skyfall mission is quite literally paving the way for human survival on another world. But here is the most crucial thing you need to understand about the SR-1 Freedom. The mission itself, as mind-blowing and futuristic as it is just the appetizer. NASA isn't just building a single isolated spaceship. They are laying down the permanent tracks for an interplanetary railroad. SR-1 is what aerospace engineers call a pathfinder. Its real job isn't just dropping helicopters on Mars. Its true purpose is to shatter the heavy bureaucratic, legal, and technological barriers that have kept nuclear power out of deep space for decades. By flying this 20-kilowatt reactor successfully, NASA proves the hardware works in real-world conditions. They establish the safety protocols, activate the industrial supply chain, and show the public that we can safely launch and operate fission reactors without catastrophic risks. Once that massive precedent is set, the floodgates completely open. This success immediately feeds into NASA's master plan for the 2030s, starting much closer to home, the Moon. Shortly after SR-1 reaches Mars, the agency plans to deploy Lunar Reactor One. If you want to build a permanent Artemis base on the lunar surface, you face a brutal reality. The lunar night lasts for 14 straight Earth days. During that time, temperatures plummet to hundreds of degrees below zero, and solar panels become completely useless pieces of glass. Batteries are simply too heavy and inefficient to last that long. Without a continuous, robust heat and power source, your multi-million-dollar base freezes solid and your life support systems die. Lunar Reactor One solves this overnight. Dropping a compact nuclear generator on the Moon gives our astronauts a reliable 24/7 power grid. It keeps the habitats warm, the oxygen flowing, and the science running, whether the sun is shining or not. It transforms the Moon from a deadly temporary campsite into a sustainable, long-term operational outpost. And from there, the scale-up is rapid and aggressive. The lessons learned from the 20-kilowatt SR-1 and the lunar reactor will feed directly into the development of true heavyweight propulsion systems. We are talking about colossal space reactors generating several megawatts of power. These won't be pushing tiny robotic probes. They will be the beating hearts of massive, multi-level crewed spacecraft. Imagine a massive orbital cruiser, heavily shielded from cosmic rays, providing artificial gravity for the crew and blasting through the void towards Mars. These megaships could drastically cut down the travel time from 9 agonizing months to just a few weeks. That is the kind of speed that protects human crews from deep space radiation and crippling psychological breakdown. SR-1 is the spark that ignites the engine of human expansion. We are watching the final transition from the era of chemical fireworks into the dawn of nuclear starships. It is the definitive first step towards building a self-sustaining city on a distant, rust-colored world. We are standing at the absolute edge of the greatest technological leap since the Apollo missions. The SR-1 Freedom isn't just a science experiment. It is the first true locomotive of the cosmic railway, rewriting the rules of what is possible and bringing a Martian metropolis within our lifetime. What do you think about NASA's radical shift to nuclear spaceflight? Let us know in the comments below. If you enjoyed this deep dive, hit that like button, subscribe, and ring the bell. Thanks for exploring the universe with Astro Trivia, and we'll see you in the next video.